Hello everyone, and welcome to Rational Science, the only site on the internet that does science and physics. You might say, is that true? Why do you make that claim, that outrageous claim? Well, we're the only ones because everybody else, every single buddy else, does particles and concepts. They move concepts around, and that's irrational. And particles, well, you cannot explain a single phenomenon of Mother Nature's with particles, rationally. So we're different because we have elongated entities. We're saying that all atoms in the universe are physically interconnected. And if you tune in here every week, you'll get an idea of, some of the things that we propose in exchange for what you hear out and see out there. And we have a different site. We also redefine what science is. Science is not the study of anything. You don't study in science. Anybody can study and not understand or be able to explain. No, science is explanation. And we've also created a foundation for the discipline known as physics. Okay, we have defined the words necessary to do physics, to do explanations of physics, physical interpretations, and no one has ever done that in 10,000 years. Okay, and so our site is a little different than all the rest out there. Okay, what are we going to talk about today? Well, we're going to talk a little bit about particles. We've been talking about for the last couple of weeks about pseudo particles and quasi particles. And today we're going to continue in that line of reasoning, if we can call that reasoning. Here's what we've been doing, just a little summary to bring people up to speed who have not tuned in the last couple of weeks. We've done quasars and pseudo particles, and what are those? Those are emergent properties. In other words, they're not particles at all. Quantum calls them particles. I don't know why they use the word particle if they're not particles. They're emergent property, and what it is actually is equations that describe collective phenomena, vibrations of many molecules or atoms or electrons or whatever. And so they look at that effect, that phenomenon of the vibration, and they call that whole vibration a particle. And they give them names, like here you have one we talked about the other day, the phonon. Okay, no, it's not like the phone. Hello, hello. No, phonon is a collective excitation of atoms forming a crystal lattice. Okay, and there you see an example. These are different phonons, the different vibrations. One vibrates that back and forth, the other one front to back and whatever. All these are different kinds of phonons. They call them phonons. Just the whole shebang, the whole vibration that's known as a particle. And it's described mathematically, and they call that equation or that solution, they call that a phonon. Okay, and then they go one step further and they start moving the phonon around. Remember, they can accelerate these things. And before that, we talked about the instanton. And what is the instanton? It's the God particle. It's not the Higgs, which was presented as the God particle. No, this is the real God particle. Why? Because the instanton gave origin to the universe. And it never appeared. It was already there, but even that's wrong to think of it that way. The way it's done, as you can see at the bottom of the instanton, it's got a circle, these circles, okay? And those circles represent space and time. So what happens, and again, this is all from a mathematical point of view. Don't try to visualize, don't try to make sense of it. It's just math, okay? Mathematics, equations, that's all it is. And what they're saying is space and time are wound around it as a circle. And since a circle has no beginning and no end, neither does space and time. That's their logic, if you can call that logic, that's their rationality. Okay, and today we have a special kind of particle. Okay, and it's also a quasi. I call them quasis because they're little quasi, quasis. Okay, and these are known as charge carriers. and you say, what the hell is a charge carrier? Okay, so let's see if I can illustrate this for you. Here's a little illustration of what a charge carrier might look like. Okay, so please focus and see if you can understand what a charge carrier is. Okay, here it goes. Those are charge carriers. Little ants going from one place to another, and then you can see they're carrying their charges. Little leaves, I guess. Okay, and this is more or less the notion of a charge carrier. The problem comes when these people say, well, we have charge carriers that go the other way and have a different charge. Those green ones that you just saw, well, we'll call them negative charges. How's that? So they were carrying negative charges. Now we have them come the other way, and I guess, I don't know, the ants are white and the leaves are red. I mean, is that what a opposite charge carrier is? Okay, and so here you have them. I guess that's what they're saying. Is that what a charge carrier is? The other one was negative. This guy's a positive charge carrier. And no, you got it wrong. The charge carrier that we're going to talk about today looks more like this. Okay, see if we can get it up there. See there? There is no ant. Okay, and whether there's a leaf, a charge that they're carrying, well, that's up for debate. Okay, but for sure there's no ant. Okay, and so the question is, what do you mean carrier? I thought a carrier was like an ant that carries a leaf, and you can say the leaf is positive. Okay, we'll let it go. We'll call it positive. And the other guy comes in the other direction. We'll call it negative. But here we're talking about charge, which is a concept, first of all. But forget about that. There's no ant. You have the leaf, if anything. If we're going to talk charge, we're going to equate charge with a physical object and say that's what they're carrying, fine. But there's no ant carrying the leaf. No ant carrying the charge. So what do you mean charge carrier? Okay, and here's a definition of what a charge carrier is. Okay, so that you can follow my presentation of their theory. Okay, this is not my theory, by the way. I can only present what they're trying to say in physical terms. Okay, and this is their definition of a charge carrier. Charge carrier, a quasi. It's another one of those quasis. Okay. Quasi particle that is free to move, carrying an electric charge. It's going to carry, over its head, like the little ants. It's going to carry an electric charge, okay? Especially the particles that carry electric charges in electrical conductors. So, electricity gives you a shock and does little fancy things like turn your light on. They're going to say those are charge carriers, okay? And okay, what are the examples? Well, the electrons, ions, and holes. Well, an electron, is a little bead. We all understand more or less that. I mean, they always represent it with a little ball, all these balls going across. Okay, so that's a flow of electron beads. We understand the mechanism, okay? Ions, same. That's the atom without the electron. Okay, so those move. Those are positive protons, okay, moving along, okay, usually by some kind of magnetic mechanism where they're accelerated, usually along a beam line. I've done that kind of work for many years. And then holes. What do they mean? You're going to accelerate a hole? What the hell are you talking about? What is this? So this is the one that I'm interested in, the holes. Okay, what are we accelerating here? It says in a conducting medium, okay, an electric field, whatever that is. There's, we don't know what a field is. Nobody knows. It's just a bunch of numbers around a central point that get weaker and weaker as you go farther away, like gravitational field. It gets weaker farther away from the center of gravity. The electric field, same thing. Gets weaker and so on, magnetism, okay? So electric field is just a bunch of numbers, vectors, that's all it is, magnitude and direction. Can exert force. Well, I don't know, force, I don't know how you can exert any force with a field because a field is just a bunch of numbers. And numbers don't usually exert forces. Again, like I said at the beginning, We don't move concepts in physics. Okay, so you got to translate this into physics somehow if you want to give a physical interpretation. Otherwise, to say that a field accelerates or exerts a force, so far you've said nothing. You said love exerts an intelligence. That's all you said. Okay, there's nothing there so far. Nothing to sink my teeth into. Okay. Exerts a force on these free particles. Okay, see now they forget about what a quasi is, what these charge carriers. Now they turn suddenly into particles. Okay, now they're going to talk about particles, and you're going to visualize always some kind of bead that goes through there. Okay, but it's when we get to the holes, that's when we're going to run into a little bit of trouble because there's going to be no ant carrying its leaf. Okay, so that's the point here. Okay. Excessive force on these particles causing a net motion of the particles through the medium. Okay, this is what constitutes an electric current. So when you get a zap, okay, like you touch a live wire, okay, they're saying that's caused by particles, and as we're going to see today, some of those particles are holes, and the holes are the leaf without the ant underneath. Okay. In conducting media, particles serve to carry charge. I don't know how you can carry charge because, you know, what the hell is charge? And so let's look at a definition of charge so that we can cover that base as well, okay, before we move on. Here's charge, okay, very simple. Electric charge, the property. It's a property, it's not a thing, it's a property. It's like an adjective, it's a qualifier. Okay, it's a modifier. A property of matter that causes it to experience a force. Okay, so here's a piece of matter, whatever you want to think of it, maybe an atom, and this is going to be a property of that particle, and the property is going to experience a force when placed in an electromagnetic field. And there you have a little picture of what they're referring to. And again, they put particles or little beads there, one positive, one negative. And you're going to look at that and say, okay, I know what they're talking about. They're talking about little particles, you know, little grains of sand or dust particles or some little ball, some little bead. And that's not what they're talking about at all. They're going to be talking about fields and properties of fields and forces. They're going to be talking about a lot of stuff that has nothing to do with physics. Okay? We don't have a physical interpretation from any of this. Okay, so just keep that in mind. It's going to be all abstract. Okay? It's all going to be mathematical concepts, which the mathematical physicists, that's what they're called, are going to introduce into physics as if they were objects. I hope you can follow, okay? Okay, so we've got a charge and a charge carrier. They're carrying charges on the backs of on their backs or over their heads like the little ants there. Okay, here's a typical circuit, okay? And those red little balls, those are supposedly the electron beads. And I haven't drawn the atoms. I just drew the beads. There's a little bit of reason for that. You know, people have forgotten what electricity used to be, which was, you know, electrons going from atom to atom, from valence band to valence band, and, you know, just moving along for whatever reason. Okay, they're incited. They're forced to move out by something called a voltage, which is defined as a difference in potential. That's all it is. So far we have no idea what physical object compels the electron bead to jump from a valence band of one atom to the valence band of another atom. Okay, this is what they're saying is electricity. But okay, we get rid of the atom. We're going to do it with little beads there, the electron beads. And what happens is when you close the circuit, okay, you have a power supply. When you close the circuit, okay, the beads begin to roll around, and since they're alleged to be negative, whatever that means in physical terms, the negative beads go to the positive terminal of the battery or the power supply, whatever you got there. Okay? So, okay, we understand the mechanism. We're understanding what they're saying. They're saying, look, there's these beads, they go around, and we're going to call that electricity. If you put your hand on the live wire, those beads will go right through you and, you know, make you tremble, I guess. You know, I've never touched a live wire myself, so I can't tell you that experience. Okay, why do I make a point of this thing about the electron beads? Well, because see, classical mechanics used to do it with atoms. What quantum has done, quantum mechanics, has gotten rid of the atom, and it does it exclusively with the electron beads. There is no atom necessary for electrical conduction in quantum mechanics. It's just the flow of beads. They talk about current being the flow of beads of electrons, and so we don't need the atom. They suggest or insinuate that you just have electrons flowing. Okay? Like if you don't need any matter, no atoms in there, all you need is just the electron, if you can call that matter, okay? So it's just the flow of beads. And just for reference, I'm going to compare it against our model, okay, just so you're aware. Okay, this is our model, and that's the torsion of a bunch of atoms which are bound to each other. In other words, they're all merged, and so the whole serpentine, as we call it, spins in situ. Okay, that's electricity. In other words, you cannot do electricity without atoms. That's the point. Okay, that's the point I'm trying to make. And you can see there's different models. You know, you can see the model from classical mechanics has this. It's not even classical because it was a turn of the century, but we can call it classical in the sense that we have an atom at least, and we have an electron. Electron was discovered, or you could say discovered, at the end of the 19th century. So I'm going to refer to that as the classical model, even though it's a quantum model, really. Okay, but the new version is without the atom, and we're saying you can't do electricity without atoms. Okay, and our electricity is the spinning in situ of of atoms that are merged one with the other. So it forms this long chain, which we're going to call serpentine, and it spins in situ. Okay. And yeah, you know, I've worked with vacuum many years. I can tell you one thing from experience, and you don't have to take my word for it. You can go to any person who works with vacuum. Any person, okay? I'm putting my hand in the fire for this. You can go to any person who works with vacuum and electricity inside vacuum chambers, okay? And once you pump it down to -7, -8, -9 torr, and just keep going, at some point, believe me, you will not get any electricity. There will not be any electron beads flowing through that empty space. And you say, why would that be so if now you don't have any resistance? Before you had all these atoms in the way, all this gas that you had in there. Now you remove all that water, all that air, all those gases, that residual gases you might have in there. You might even have back streaming from the pumps or whatever. You can remove everything. You have a perfect vacuum in there. The electrons that go through the circuit now have freedom. You know, mean-free paths should have increased exponentially. You have no resistance to the electron flow. You should have electricity flowing there like crazy. And it's the other way around. Once you get into the -7, -8 torr range, there is no electricity flowing. You might have some arcing here and there, I don't know. Arcing is just a little bolt that Zeus sends into your chamber, and that's it. But it's not going to be a continuous current. You can't do it. It's simply impossible. So no, electricity is not the flow of electron beads without atoms, which is the quantum version of today, which is what people talk about, and that's what they write. They just talk about the electron flow. They forget about the rest of the atom. Okay, and that's where the danger comes in. Now, you need atoms. You can't do electricity without atoms. Sorry. Okay, here's, but we can all understand the flow of electron beads, but that's not what you have. What you have today is also a step on top of that. You need to explain the positive current as well. Okay, and I'll show you why in a minute, okay? But you need to explain the positive current. What do you mean positive current? I thought a current was always negative because it's always electron beads that flow from, you know, the cathode to the anode, goes to the positive terminal, right? Well, no, this is the version, I'm going to show you in a second here. This is the version of holes, okay? And so what you have is the holes are flowing from left to right, and they go to the negative pole. They go to the cathode. And those are true holes, just absence of electrons. That's what you're staring at. The electrons are allegedly flowing towards the left, towards the positive pole, and when an electron moves from one atom to the one to the left, the hole has moved to the right. In other words, the absence of an electron has moved to the right. They're going to call that absence of an electron, they're going to call that a positive hole. Okay, so we have negative electron beads going to the left, and you have positive holes going to the right. Okay, and yeah, we can get rid of the electron altogether. I guess we can just do this with holes. We can probably even get rid of the atom. Those are silicon atoms, by the way. There's a reason for that. Typically, it's in semiconductors, the business I worked in, where all this is used. Okay, so what they have is silicon. Silicon has 4 electrons in its outer shell. Okay, and with 4 other atoms, silicon atoms nearby, they fill the outer valence band with 8 electrons, so they're satisfied. They don't need anything else. But if you put in there, if you happen to what we call implant, okay, we're going to implant an atom in there that is either phosphorus or boron. If you put boron, what you have is 3 electrons in the outer shell, and so it's missing an electron. And that electron is going to cause electron flows inside that lattice. In other words, that crystal lattice. What you're going to have is electrons from one silicon move to that electron that's missing in the boron. And vice versa. If you put phosphorus in there, phosphorus has 5 electrons in its outer shell, and it's going to be a donor. It's going to donate one of its electrons, which it has no idea what it's going to do with it, and that electron is going to be free to flow in the opposite direction of holes. So we're going to have holes moving in one direction, and we're going to have electron beads, negative electron beads, in the other direction. Holes are positive, electrons are negative. Okay, so this is the notion that we have in semiconductors processing. We have holes and electrons. What is a hole? It's the absence of an electron in a valence band, in the outer shell, okay, of an atom. Okay, very, very scary, because this is what you're staring at here, okay? You ever see Bugs Bunny? He moves the hole around. And these guys are going to move a hole through the desert, okay? They're going to move the rabbit hole, so to speak, okay? Very scary stuff, okay? That's what they're proposing. They're proposing the hole moves. Here's another analogy of what they're talking about. You heard of the puzzle of the 16 squares, okay? And you move the electron to the right. We're going to call these squares electrons, okay? And if I got to do this right, I moved it to the left, and I created a hole to the right. And if I move the next one now, let's see if I can do this by looking at, I move that one over there. Where did the hole move? Well, the hole moved to the left again. Okay, and I can continue doing that. Okay, here it is again. I can get it. Okay, and you can see the hole is always moving to the left. And what they're saying is the electron is the little square. And the hole is the hole there. It's the here, the absence of an electron. Okay, and so you can see there's a flow of holes, and they're going to call that a current. They're going to say it's like a positive current. Okay, so this is how they're going to do this. Okay, just keep in mind what we're doing here. We're saying that it's the absence of an electron, and as the electron creates an absence of an electron in the previous atom, what filled that is a hole. In other words, what you would be seeing on a screen is electrons going one way and a hole's going the other way. Okay, that's the notion. Okay, why do we need this? Well, we need this, for example, in semiconductor processing. You need this because, I took a course, very tough course called device physics. And they go through a lot of calculations. It's just murder on the math. You got a lot of equations. You have calculus, etc., that you have to apply. And what you're calculating is how many carriers you have to create certain electrical effects. Okay, that's in a nutshell what you're doing. And what are carriers? Well, you have one chunk of matter, silicon, to make it simple. So they have gallium arsenide, they have some other stuff. But let's assume we have silicon. And again, you're going to dope that silicon, in one case with phosphorus, and you're going to have it negatively doped because it's got an extra electron in its outer shell. And the other one you're going to dope with boron, which has it has only 3 electrons in its outer shell. So it's going to be an acceptor type of atom. And so you have this material with phosphorus, donor, negative, and you have this other material with boron, positive. Okay? What happens when you put them together? Well, as soon as you merge them, you create what is known as a depletion zone in between. There's a junction there, and that junction is known as the depletion zone. Why? Because what happens is the electrons get filled in all that region. Okay, so you have neutralized all those atoms at a certain distance from the junction. Okay, and it looks more or less like this. Let's see if I can show you this. Okay, and here you see it. What you have is a p-type region, that's the boron, and you have the n-type region, that's the phosphorus. Okay, as soon as you touch those two pieces, those two chunks of matter, what you create is that depletion region at the bottom. And what is that? Well, you have a negative ion from a filled hole, and you have a positive ion from a removed hole. Okay, so you have this region that is kind of neutralized. Okay, and the only way you can get past that barrier is applying a voltage to the ends. Okay, and at some point you have to have strong enough voltage to create a current to go through that. Okay, that's how they can regulate. How a diode or how an interface in a transistor works. Okay, that's essentially how these things work in general terms. From an electrical point of view, what you have is a little thing that has a little piece of matter. On one side you have phosphorus, and the other one you have boron. Boron is positive, phosphorus is negative. You put them together, you create a depletion zone, and that creates sort of like a barrier. And the only way you can overcome that barrier is by applying a current to the terminals, right? Voltage, and you have current flowing through that depletion region as soon as it's high enough. Okay, as soon as the voltage is high enough. Okay, and you can control that. They have what is called a bipolar transistor, where you control the guy in the center. Okay, also MOS, metal oxide semiconductor, where you control the guy in the center, and by controlling the voltage in the guy in the center, you can control how much flow there is, from right to left, for example. Okay, but that's why they needed to create this whole thing, because they had to explain how you create a depletion region. Okay, the depletion region, all you have is really assuming there are such a thing as electron beads. Well, it gets saturated. That whole region, kind of blends in and turns into this neutral region that you have to overcome with voltage applied to the ends, to the terminals. So we create the hole, and we had to, the quantum mechanics had to invent the hole. And the hole is actually the absence of matter. If you want to consider an electron, a negative electron bead, a piece of matter, well, the hole is an absence of matter. That's what it is. And because the other guy is negative, they put this one as positive. So one question you should ask yourself is whether a positive hole, right, is attracted by a positive proton. I mean, you have this boron atom, you have this phosphorus atom, right? And they have protons in, the planetary atom, which they still use in quantum. They have these protons in the center of in the nucleus, in the center of the atom. And you have this hole. If the hole is positive, right, because you remove the electron, and that's what a hole is, the absence of an electron, and they call that a positive particle, quasi-particle, pseudo-particle. Is that pseudo, quasi, attracted, positive pseudo quasi, attracted to the positive proton. You have a positive nothing, and you have a positive something in the center of the atom, okay? Is that attracted or repelled? Should be repelled, right? You would think. But you can't repel nothing, and I guess you can't attract nothing either, so maybe it's a meaningless question in quantum mechanics. Okay, so let me give you the notion here. Some people say, well, I'm suggesting that no one understands quantum mechanics. And a lot of people criticize me and say, well, Bill, maybe you don't understand quantum mechanics, but everybody else does. You have people like Feynman, he tells you in your face, look, we don't understand it. Here he is. He says, I think I can safely say that nobody understands quantum mechanics. Do not keep asking yourself if you can possibly avoid it, but how can it be like that? Nobody knows how it can be like that. The more you know how strangely nature behaves under the particle hypothesis, okay, the harder it is to make a model that explains how even the simplest phenomena actually work. So theoretical physics, mathematical physics, has given up on that. And you tell them this, you show them this, you say, look, this is Feynman, he's a Nobel Prize, 1965 Nobel Prize in Physics, mathematical physics, mathematics, and he's telling you they don't understand. They say, well, you don't understand what he's saying. You're misinterpreting what he's saying. And they go through this runaround saying, no, see, he tried to say something else and you didn't follow up on what he was saying. No, he's telling you in your face that you don't understand it, that nobody understands it. Niels Bohr had already said that. Werner Heisenberg, these are the founders of quantum mechanics, they all said the same thing. Nobody understands quantum mechanics. And these people say, no, they do understand, or maybe they're too modest to recognize it, or because how can it possibly be that they don't understand and they invented the bomb, for example, and we have all this technology? Well, again, technology has nothing to do with science. Okay, these are two different aspects of human activity. Developing gadgets, you don't need to understand what a field is. You don't need to understand what light is. You don't need to understand what energy is. You just do stuff in the lab, stuff that you don't see, that you can't touch, and you see certain effects, and you're going to use the effect in some way that is good for mankind. Okay? So you don't need to understand the fundamentals of what's really going on in that secret world, invisible, intangible world of Mother Nature's. You do not need to understand that, okay, to do technology. So you can invent the bomb without having, without understanding exactly what's going on at the atomic level. And these people explain it with particles, but when you put them against the wall, they say, well, we don't understand it either. And they're telling you that they don't understand it. They tell you over and over that they don't understand it. And the answer is, well, you wouldn't have invented the bomb if you didn't understand it. Okay, so this is a problem. This is a serious problem because people don't understand that the mathematicians don't understand because they cannot explain in a rational manner what's happening at the atomic level, for example, in the case of an atomic bomb. Okay? And again, the Iranians don't have a bomb. Apparently they don't have a bomb today, and their mathematicians are just as good as the guys in the West. So no, the fact that you know a lot of math and that you can describe and that even if you knew what happens at the atomic level, doesn't mean that you can invent the bomb, because that's done by trial and error. In a lab, you do certain things and you have to put it together, you have to create a device, and that's got nothing to do with science. Science is about explaining. Tell me what a field is. Tell me what energy is and how it works. That's what you need to do. You got to figure out how the invisible, intangible world of Mother Nature's is. That's what science is about. And that's what we don't have today. Certainly not from quantum mechanics or relativity or string theory. Okay, so here's my summary, my conclusions. Okay, and this has to do with overall quantum and in particular the quasi particles, especially the hole. Okay, here's the summary or the conclusion. Okay, a hole is alleged to be a charge carrier, whatever a charge carrier is. What is a charge carrier? It's labeled as a pseudo particle. Is a charge carrier a particle at all? Why do they use the word particle? Is it to confuse you, to mislead you, so that you think that you're talking about a little bead? Is that the point? To give it some measure of physical interpretation to their abstract equations, to their fields, to their waves, to their pseudo particles? Is that what it's all about? The term carrier insinuates that a whole is carrying and delivers an object. You know, the little ant with a little leaf. We all understand that. The ant is delivering, it's carrying and delivering a leaf. We all understand that. Okay? We see the movie, we understand it. But to say that a whole is a charge carrier and carries what? Charge over its head? Is that the language that we're seeing here? Is that what the language represents? Okay? So a hole is an empty slot left in the valence band by an electron bead that drifted to another atom. So it leaves a hole behind. They call that hole a something. And they put a little positive signs to distinguish it from the negative electron, which is a bead. So we have a negative bead and a positive nothing. Okay? And the positive nothings flow. That's what a hole is. That's what the quasi pseudo particle is. A nothing that is flowing, that's got charge, positive charge, whatever that is. Holes are alleged to be positive because they travel in a direction opposite to electrons. So the electron is negative because it goes to the left. The other guy has to be positive because it goes to the right. Okay, is that what positive and negative mean? Is that the same thing when we say that a proton is positive? Does it mean it goes to the right while the electron goes to the left? Okay, I mean, if they're positive and negative, you would think that they attract each other, right? I mean, that's the catechism of quantum mechanics. Positive attracts negative. Okay? Depletion layers in diodes and transistors are explained using the whole concept. Okay, so you need, in fact, if you took like device physics, you get all these gazillions of carriers that you have to calculate. How many carriers you need to put in there to create certain electrical effects. And so these are real in the sense that that's how it's taught. You're taught that you have carriers, whole carriers, you know, they carry charges, and you have to count how many carriers there are, how many ants there are, how many leaves that they're carrying. That's the kind of mathematics you get taught in college. Okay, it's called quantum mechanics. And the physical interpretation of quantum is irrational. And proof of that evidence, you like proof and evidence, demonstration, persuasion, go to Mr. Feynman, he'll tell you, we have no idea what we're doing in a lab. They can describe it mathematically because they see something happening, and they describe the visible stuff mathematically, and they kind of simulate that empty space where they can't see or touch. They simulate that with particles. And that's where they're going to apply their equation to. They say, well, there's so much speed between A and B, so we're going to say that particle took, 5 seconds to get from A to B, for example. And so they're going to assume it's a particle, a one-way particle, and they're just going to describe its motion, or its energy, or how much force was needed, or etc., or how much mass it has. That's the way it's done. Okay? Are there particles? Does that mean there are particles? No, there aren't particles because Mr. Feynman has just told you, and so did Mr. Bohr and Mr. Heisenberg, and they tell you that don't try to visualize this. Don't try to imagine it with particles, but we're going to use the word particle anyways because a particle is just an equation. In the case of quasi-particle, it's more than that. It's just an excitation. You get excited. Okay, let's go with the questions and comments this week. Okay, we had quite a few of them. I'm going to try to rush through them somehow. Here's the first one. Okay, yeah, this fellow has been going on for a couple of weeks. He says, if we are going to talk physics, there is an actual dictionary we are using. The most popular one is a dictionary of physics. He was trying to define the word object, which we think is crucial to understanding physics. You can't do physics without an object. So he tried to define it, and he says, well, you know, physics definition of object. He says he got this out of a dictionary, a scientific dictionary. It says identifiable collection of matter. And I say he didn't get it from a scientific dictionary. He got it from the Wikipedia, which says exactly the same thing. An object is an identifiable collection of matter. So I guess he considers the Wikipedia a scientific dictionary. And so I asked him, he said no, he got it from somewhere else, that it wasn't from the Wikipedia. So I said, well, you can put a link, and we can look and judge objectively whether you got it from a scientific dictionary. And he says, well, YouTube isn't letting me post links. And so he doesn't have to. He can just separate the little h from the TTPS, and he can put that in there, and we can still, we can do that. We can put the h together with a TTPS, find out where he got it. Well, he never showed up again. But he just said, so you have to do your own search. You can simply Google physics definitions. So when you go out there, and you can do that, you don't take my word for it, please. Go out there and do a physics definition or scientific definition of the word object. Again, we can't do physics without objects, so you would think it's one of the crucial words that they're going to define in physics. The first thing, you won't find it in any textbook of physics on the planet, and has never been in any textbook of physics on the planet. No one has ever defined the word object, and you can't do physics without an object. So that should make you think that maybe all these mathematicians are not on the right track. And it's very simple to understand why. Mathematics has nothing to do with objects, and all the so-called physics for the last 400 years has been done by, not physicists, by mathematicians. Okay, so it's the mathematicians who've done so-called physics, and they never found a need to define the word object because they don't use objects. They just do equations. That's why you won't find a definition in any dictionary of so-called physics or science. But when you look it up, you'll find those two definitions, essentially. You find the one in the Wikipedia, which I just mentioned, collection of matter, okay? And then the other one, very popular, more popular still, which is you'll find in actually all so-called scientific definitions, scientific dictionaries that have the word defined, because half of them don't, and I'm going to show you that in a second. And it says anything that is visible or tangible and is relatively stable in form. Well, the first problem is the word anything. Anything is a synonym of object, so you can't use the word anything to define object because a synonym is a circular definition. So anyone who uses the word thing or anything or something already has bombed out. You can't use that word to define the word object because that's the word we're trying to define. Something, thing, and anything. And then visible and tangible. They think all these people just got it from the same place or have the same notion, and that's that an object is that which you can touch or see. And the problem with that, first of all, is that you need another object to do the touching and seeing, which makes the definition circular again. You need two objects to define one object. You need to carry out an experiment. In other words, until the asteroid doesn't hit the moon and touches it, we don't know if the asteroid or the moon is an object. We got to wait until that asteroid really hits the moon, and then we can call the moon an object. That's the problem, okay? And here is what you'll find out there. Well, no, here's my challenge to what this fellow said. First, there is no dictionary of science that defines the word object, thing, something, entity, all those synonyms, right, in a rational manner. Meaning, if you're going to use the word anything or you're going to say visible and tangible, you're already bummed out, okay? And collection of matter, again, that's mereology. And a table is not a collection of matter any more than an elephant is. In other words, collection of matter is not a physical object. Okay? So you don't say that a table is just a bunch of particles, or an elephant is a bunch of particles. That's a collection of matter. That does not constitute an object. Okay? What is a definition? It's a limitation placed on the use or extent of a word. Okay? And a rational definition was one that can be used consistently, meaning rationally, scientifically. Okay? And there's the definition of object, that which has shape. He who doesn't like it has to become up with a better mousetrap and be able to defend it. It's not just a question of saying, I copied it from a scientific dictionary, even if you did. It doesn't matter because you got to defend it. You know, anybody can copy. That's not science saying, oh, I got a dictionary from, I got a word out of a dictionary. What is that? If the person who wrote it is mentally retarded, does that make your definition rational? Okay. And here are dictionaries that I checked on the internet. Okay, I checked several more, but I only put 6 here, 3 on the left and 3 on the right. The 3 on the left did not define the word object at all. Okay, so you won't find it in there. They talk about physics and other stuff, but they didn't define the word object. And you would think that if they're going to talk about physics, at least they got to have a definition for the word object. The ones on the right, they all have the same thing. They all go back to the something and to the visible and tangible, or see and touch. Okay, and you can see they're all the same essentially. And no, those definitions are unscientific. They cannot be used consistently. They are irrational because they rely on an experiment and they require a second object. So there's many problems with all those definitions. And they're all the same, essentially see, touch. That's why the see, touch criterion or criteria cannot be used to define the word object in physics. In ordinary speech, that's another issue. Okay, along the same lines, another fellow asked, he says, because we say a square is an object. Why? Because it does have shape. Okay, and it's not the notion of object that you have in ordinary speech. People confuse the ordinary speech with scientific language. What do you mean a square is an object? Yeah, in ordinary speech that sounds strange. In physics it doesn't. Because what's the definition of object? That which has shape. Does a square have shape? Well, look at that square. Does it have shape? And the fellow says, thinking of a slight modification to your otherwise excellent definition for object, equal that which has shape and at least 1 unit of mass. Okay, so are we gonna, should we weigh the square to determine whether it has at least 1 unit of mass? Is that what he's suggesting? He says we have to carry out an experiment to determine whether it has mass or not. We got to weigh it or however, or count, or I don't know, depending on the definition, because we have several definitions of mass, and he would have to tell us which one he's using. What do you mean by mass? I mean, here we have, where do we have it here? These folks say that we don't know, we have no idea what mass is, okay? And they're Wheeler and Taylor. Wheeler died a couple years ago. And they wrote in a book, nature does not offer us any concept as the amount of matter. So if that's what you were taught in high school, you got it wrong, okay? These people who outrank you, for sure, they say that amount of matter is not the definition of mass. They're saying history has struck down every proposal to define such a term. Even if we could count number of atoms or by any other counting method try to evaluate amount of matter, that number would not equal mass, okay? And I don't want to complicate it, but when you put special relativity, okay, into the picture, and they talk about traveling at the speed, near the speed of light, they say mass increases. Well, that sounds like weight. It sounds like pressure on a scale. You know, the faster it goes, the more pressure on the scale, the more you weigh. Is that what mass is? Relativistic mass? It's just weight? So again, all these people, you got to define what mass is, because there's different notions. I don't care which one you use, but whichever one you use, you're going to run an experiment. And you're going to use another object, which in this case is a scale. So no, anything that involves motion is not a rational definition for the word object. And here are all the others so that I can save you some time in case you want to try it. Okay, let me put it over here. Okay, none of these definitions will pass. They're easily debunked. Okay, it can't be that which you can see, touch, hear, taste, smell. You can't use the senses to determine the definition of the word object, to define the word object. You can't use the word mass. Okay, it's not mass, it's not volume. Okay, can move, made of parts, mereology, which is essentially what this fellow is saying when he's saying mass. Also, if he's saying 1 unit of mass, he's saying it's got parts. Okay, It's not that which you visualize through time, okay, the temporal parts as is known, mereology again, parts of whole and temporal parts, etc. It's not which is extended, because extension is a verb, okay, so you have to extend it to find out if it's an object, etc. That you can use in a sentence. You can use the word orbit in a sentence. Orbit is not a physical object. Orbit is a verb for the purposes of physics. It's a noun in ordinary speech. It's not a noun in physics. You cannot talk about the orbit of Jupiter. No, in physics we say it in reverse. We say Jupiter orbits, and orbits becomes a verb. Okay. Same with orbital, by the way. They say lots of orbits make an orbital, and an orbital is a physical object, a noun. No, not in physics. Okay, maybe in religion of quantum, not in physics. Has color, is 3D, and it's got to be a standalone object. You should be able to point to the object that you introduce in physics. It's got to be standalone. It can't be, like I always say, the halo of an angel or a field of a magnet. Field is not a physical object. It doesn't stand alone. You can't use plasma as a physical object. There's no physical object called plasma. Plasma is a phenomenon. It's a dynamic concept known as plasma. You have to ionize the atom. In fact, many of them. So plasma is not a physical object. You can't point to plasma because whatever's in that frame of the film, in just that frame, is not moving. It's not being ionized. You need to see at least 2 frames to understand the concept plasma. Okay? And it takes people in the electric universe 10 years to understand what I just said. Okay? So just go over it one more time. Maybe you'll figure it out one of these days. Okay, another fellow says, ropes don't exist. I don't know what you mean by exist. Your ropes are a concept. I don't know what you mean by concept. See, this is a rope. What do you mean a rope is a concept? That looks like an object. It has shape. So a rope is an object here and in the land of the Klingons on the other side of the universe. So I don't know what you mean by ropes as a concept. Again, you got to define what exist and concept is. Otherwise, you said absolutely nothing. Okay, and here's another fella, and he says the following. He says, get this up here. He says, one peculiarity in this electromagnetic rope, I guess he says, hypothesis, is that the thread does not go through itself, but the rope does. Aha. Consider the very model for magnetism in the hypothesis, where the threads collide to push or to pull, thus creating the effect we see in magnets. Okay, so he's saying that the threads, okay, they hit and push each other away, or they go, I guess I pulled this out a little bit, just so you can see it, what I'm saying here. So if you go in this way, the threads, gazillions of threads just pushing each other away, that's the repulsion mechanism for magnetism. And then when you turn the magnet 180 degrees, now this one's pulling, these threads come down this way, these are going this way, so they're both going, in this case, I guess from your point of view, it's counterclockwise, yeah. And so this one comes down when this one comes up, and that's when the attraction occurs. And that's the mechanism of attraction. And so he's saying, well, you know, the threads are going, he's saying the threads are pulling on each other. And no, the answer is no, and so let's clarify that for him. Let me read the rest of it here, because he raised an important question. Clearly, a single thread of the rope is the active element there and either cannot go through itself or does so with some resistance. Resulting in the push or pull forces. Yeah, you said that. That's the critical part. With some resistance, there is friction. Okay, and let's go over that. Okay, it's an important issue, and I think it needs to be clarified. He also added the following. Okay, here, let's continue with what he said, because he got the right issue in here. The rope seems to have no difficulty at all in crossing itself. It could be argued that were the thread able to go through itself, it would not be able to form the rope, since the thread would slide right through the other one. There must either be extreme resistance to cross or total exclusion. This begs the question, why would the rope provide for what the single thread cannot? Is it another property of this single piece object? Okay, very, very good question, I think. Okay, it needs to be clarified. Let me put it over here. So let's see how we answer this. Okay. And the first thing I want to mention here are the properties of the thread, what we're proposing. Okay, so these are the properties we're proposing for the single thread that makes up all matter, underlies all matter in the universe. All atoms, all ropes that interconnect them are made of the same thread. There's only one thread, closed loop thread in the entire universe. That's the notion we're proposing as an assumption, as a starting assumption to be able to explain later on the theories that form what we call thread theory. Okay, so here it is. These are the properties of the thread, of the single thread that underlies all of matter. It resembles the thread of our macro world. See if I have a little thread here tied to a little. Okay, that's a thread. Okay, and so it resembles this. Okay, that's what we're talking about. We're suggesting that there's a single thread. Here's another example maybe of that. I hope you can see that. That's a rubber band. Okay, it doesn't stretch. Okay, so the stretching is not part of the properties. Okay, it's made of a single piece and it doesn't stretch. Okay, but you can think of the thread as this. That's what it is. Okay, so very simple, closed loop thread. Very simple. As simple as you can make it, that's what it is. That's what we're proposing. Single thread, closed loop thread. Okay, but here are the differences with the thread of ordinary speech of our everyday macro world. Okay, it has the shape of a macro thread. Yeah, it is thus an object because it has shape, right? The rubber band, this rubber band has shape. Okay, if it has shape to you, well, that's what this thread is, and so it has shape. It is an object. Okay, so I hope that's clear. It's an object. Very simple kindergarten stuff. Okay, don't make it any more complicated than it is. It's just a single thread, closed loop thread. So closed loop, it's made of a single piece. And this is where the issue that this gentleman comes up with, because we have the issue, if it's made out of a single piece, we can explain some things, but not others. Okay, according to our macro world notions of everyday experience. Okay, so our everyday experience comes up against this. Why? Because we don't see things going through things in our everyday world. And it turns out that, you don't have to take my word for it, go to quantum mechanics and they say that particles go through particles. And nobody questions that. And you say, what do you mean particles go through particles? Well, I showed it the other day, just an example, okay, that, where is it here? Here you have, here you have light. Now, let me get this out for a second here so that I can show this to you, okay. Here you have light, okay, and here you have another light, okay, two lights. And I can have these lights go through each other. In other words, you know, the lights are crossing each other. They're not interfering. There are no particles jumping away from each other. Try to do that with your bathroom shower. Take two bathroom showers or two hoses. Okay, just take two hoses at home and have water pouring out of them, great speeds, and just cross the waters. You know, cross the hoses, the paths of the water. And you'll see that you get splashes everywhere. The particles of water, whatever water is, right? Some molecules, some atoms, they jump out of there. They jump out of that collision. There is a collision, okay? And in the case of light, you don't see that. And again, here you have another example. Gravity. Invisible, intangible. You don't see anything below the pencil. You don't see or touch anything above the pencil, okay? And the pencil always goes to the floor. And you say, well, hold it, it always goes to the floor. Why does it go to the floor? Well, I think there's only two possibilities because we only have two forces in the universe. One is push, the other one is pull. It's push or pull. Okay? The mathematicians invented four forces, four horses of the apocalypse, as I call them. There's only two forces. That's all we can imagine. It's either pull or push. You have the gluon and the graviton, they're pull forces. And the, the weak and the electromagnetic, they're both push forces. And so we have pull and push. So I don't know what other force there is that you can imagine. And the issue is you have gravity, and when you have the Earth go around the sun, at some point it gets in the way, it eclipses, so to speak, Jupiter and some other planets, Uranus, Pluto. It gets in the way between the Earth, between the sun and this other planet, right? And it doesn't cut the effect of the sun on those. If anything, it adds to it, but it's not because the Earth gets in the way between the sun and Pluto that Pluto says finally and escapes out of the solar system. So whatever gravity is, it goes right through the Earth and all the way to Pluto. So gravity is invisible and intangible, just like light is. Okay, so we have invisible and intangible light, invisible and intangible gravity. We have to explain those properties. Those are the properties of Mother Nature, and we don't have any such thing in our macro world, such as those invisible mediators that Mother Nature uses to do gravity and light. Am I getting through? Okay? Okay? Let me say that one more time, just in case, because some people maybe have not understood. I'm saying that gravity and light are mediated by a physical object, that which has shape, an object that is invisible and intangible, which again destroys the definition of see-touch for the word object. Okay, so see-touch cannot be used because here we have an object that has shape, if it's an object, but cannot be seen or touched. Okay, and so that's what we have to try to do. We have to imitate Mother Nature's world, Father Universe, God, whoever you believe in. Okay, so the issue here is the following. We're going to use the thread, and in order for the thread to be an object, it has to have shape. I think I've established that with a rubber band. It looks like that rubber band, except it doesn't stretch. Okay, make sure it doesn't stretch. People think it stretches. No, it doesn't. It's made of a single piece. It's malleable. It's malleable, and you can't touch it, at least not in the macro world sense. Okay? It doesn't have the property of touch that we have in our macro world. Whether there is some kind of touch, some kind of friction at that level, that's what's going to be an issue here. You know, is there a friction? And can it go through each other? Well, it can go through each other in a sense, much like a river can go through, or water can go through water, or air can go through air, you know. And again, you know, in the real world, particles exclude other particles from their location because they're made out of atoms. But here we're talking about something so fundamental that it doesn't have the property of touch that we have in our macro world, meaning that one thread cannot exclude another thread from whatever location it has at that moment in time, if you could talk about location at that level. Okay? So the thread goes through a thread. But this fellow said, well, if it goes through a thread, how can you make the rope? Which is a very good question. Okay? And believe me, I thought about that a long time when I wrote my book originally. Okay? It was a big problem. Okay, so first let's get back to the, make sure we understand the properties of the thread. Okay, here it is one more time. Okay, so we cover those, and closed loop, made of a single piece. It's not rigid despite that it's made of out of a single piece. Okay, and you say, hold it, anything made out of a single piece has to be rigid. Well, keep in mind, we don't have any example in our macro world of anything that is rigid, meaning made of a single piece. Everything is made of atoms. Okay? And so if everything is made of atoms, we don't have anything made out of a single piece, even the atom itself, because again, well, there are different versions, but if you take the quantum version, for sure, you don't have a single piece. So we don't have single piece, especially in our macro world. And so we don't have perfect rigidity. We don't know what rigidity is. We have no way of imitating anything in the world of rigidity. Rigid does not necessarily mean made of a single piece. I mean, yeah, that is a good definition for rigidity, but in Mother Nature's world, she's got this thing made out of a single piece, but it's not rigid. It has the properties more like a rubber band of an ocean, you know, water moving around. It's fluid, okay? we're talking again, the fundamental thing that makes everything else. Okay, so let's keep the context in mind. Okay, it goes through itself. Okay, it's invisible and intangible, especially in our macro world. Okay, we have no way of seeing. We can't see atom. We can't see a hydrogen atom, which is in the angstrom level. Okay, which is to the -10th of a meter. Okay, so we're talking about something you can't see, and this thing is much thinner than an atom. If you take the diameter of, or even the radius of an atom, a hydrogen atom, the smallest atom, this thing is, you could say, infinitesimally thinner than that. It's just something vanishingly thin. That's why perhaps it has some of these properties, or at least those are the ones we're going to assign to them if we're going to explain Mother Nature's world. And Mother Nature's world is this intangible, invisible world of objects. Hopefully she does it with objects and not with spirits. Hopefully she does gravity with some kind of object and not with hocus pocus. Hopefully she does light with some kind of object, invisible and intangible object, and not with spirits. And so when you use the word energy, you're saying spirit. And when you use the word field, you're using the word ghost. And when you're using the word mass or wave, you're using the phantom. You're using concepts as objects. We have to identify the physical object that underlies light, gravity, magnetism, etc., electricity. So you can't say, well, there's no object there, because then you are introducing black magic. Okay, let's hope that's clear. And many threads produce the tangibility and visibility that this gentleman talks about. So yeah, when he qualified that, he essentially did the right thing, because he came back to rationality. And I'm going to give you an example now of that. One is the Rutherford's backscattering. If you look at the quantum atom, they tell you that almost all of it is empty space. Just like the brains of the people who created that. It's almost empty space between their ears. And the reason they thought it was empty space is because of this. Here they had the atom. Okay, I'm going to show you this in steps. Here's the atom, the quantum atom. Okay, you think of that electron ball going around the proton center. Okay, so that's essentially the model that these people propose. Even to this day, they have this cloudy model. Essentially what they have is a perimeter or a volume, and the electron bead for some reason cannot escape that volume, and for some reason it doesn't also fall to the center of the atom where the proton is, even though one is positive and the other one is negative. So we don't know why that electron runs around and doesn't leave the atom or fall to the center. That's the first thing that quantum mechanics cannot explain. And if they cannot explain their most simple atom, they cannot explain absolutely anything rationally. And that's where we are today. Okay? We don't have an explanation. That's why Mr. Feynman tells you we don't understand any of this. Okay? And Bohr said the same thing, Heisenberg as well. Okay, so what do we do? Well, Mr. Rutherford went in there and he bombarded that with neutrons, okay, essentially. Okay, so here it is. See if we can show it. Here's the neutron, and it hits the center of the atom. In other words, neutron hitting proton, and it bounced back. He said it was like throwing a cannonball or whatever at a paper tissue and having the cannonball bounce back. That's essentially how he described what he observed. And he did not observe it. What he simply saw was the visible stuff, and he did not really see the interaction or what was going on inside the atoms. Okay, he just said some of the stuff that I threw at it bounced back. That's all he could say. And from that, he declared that the atom was mostly empty space, because what he found out was that some of these neutrons, they just went right through it. Okay, they just went through the atom, especially when it was thrown directly at the atom. The whole crystal lattice, these things went right through. And so he said, most of an atom is empty space, because the neutron just goes right through, and only when it hits the center do we have something there, and he called that something the proton. Okay, so this is the train of thought that Mr. Rutherford went through in 1919, And this is where we got the notion that an atom is mostly empty space. Okay, again, empty space is what quantum mechanics has. The mechanics have in between their ears. Okay, so here's the. Let's see if I can get it here. Here's the rope version of backscattering. Okay, and so we start by saying that we start by showing the atom and the neutron. Okay. And the proton is on the left side. You can see the proton is a little different than the neutron. Why? Because it's got a region where only threads are going to the center, whereas in the neutron, the ropes go right through the center. So the difference between these is ropes versus threads. Okay, what you have is convergence of single threads and convergence of ropes. That's the difference between a proton and a neutron. Why does an atom have charge? Why does it have this thing they call positive and negative? Because that blue circle that surrounds the proton expands and contracts. In other words, it eats the rope and it releases a link of the rope. So it goes back and forth. That's the quantum jump that torques the rope, and the rope is light. Okay, very simple mechanism, baby stuff. Even a baby can understand it. Whether you believe it or not is immaterial. We're trying to explain a mechanism here so that you understand it. And here again, you have the atom and the neutron. Okay, so now we're going to do this this neutron bombardment, this backscattering. Okay, let me get it in here. Got them all the way at the bottom, so got to raise them up here. Okay, here you have neutron going right through a three-dimensional atom. Essentially, if it hits in the center, like center of the neutron with the center of the atom, it's going to bounce back. That's what Rutherford verified. And if instead it goes through any other part, the ropes go right through the threads. Okay, so again, the thread can go through the thread, the rope can go through the thread, and the rope can go through the rope. Okay. And so that's what we're going to propose. And again, Rutherford the only way he could get around that was saying the atom is mostly empty space. But then he cannot explain why the little bead doesn't fly out of the atom or fall into the nucleus. And they never do explain that. And that's the only thing that quantum has to explain. That's the only thing they had to explain in 100 years. And they cannot explain that, because for that you need physical objects. You would have to tell me what physical object prevents the electron from flying away, or if you want it in a different way, what physical object lies between the electron and the proton? Well, what is that space there, that empty space? If it's empty space, why doesn't the electron fly away? And so people say, well, it's a field. Well, a field is a concept. That's a bunch of numbers. So you can't say it's a field because a field is not a physical object. You got to tell me what physical object is in there. Other people say it's the ether. My God. So you got all these bird brains out there trying to figure out what physical object is between the electron and the proton. And no, the ether, if the ether is a bunch of particles, which is what it is, what the definition of it is, unless you can come up with something better, you cannot explain how a bunch of particles, a sandbox, holds one thing tied to the other. Okay? Or why doesn't it fall to the proton? Because of the sandbox, we could probably understand. There's a bunch of sand in between. Fine. Why doesn't it fly away? Is there sand on the outside also of the atom? So, yeah, you can't explain it with a sandbox either, if that's what you propose. Otherwise, you got to tell me what the ether is, what the field is, what this energy is. You got to identify the physical object. Okay? Okay, and here's my explanation for the other issue that this gentleman raised. And this is an analogy, okay? Please take it only as an analogy. I'm trying to explain why one thread does not go through another while they form the rope. If you take just a piece of cotton, okay, I just want you to understand the concept here, okay? Again, we're trying to figure out what Mother Nature has in that invisible world, okay? And so if you take a piece of cotton, you can pull it and you'll see that it'll break up. The strength of that is not very, it's not very strong. There's not much resistance to you pulling cotton apart, okay? But if on the other hand you torque the cotton around itself, well, it's much stronger. Okay, in fact, one guy explains that pretty much. He says cotton is made of a lot of tiny fibers. If you pull a cotton ball apart, you'll find that they are very skinny and quite short. These fibers aren't stuck to each other. They are all individual pieces. What's holding them together is tangles and friction. Okay? When you unroll and stretch a cotton ball, you start untangling the fibers, which is why the cotton ball becomes so fragile. When you start twisting cotton, you do two things. First, the fibers get wrapped around each other, which helps to tangle them again. Second, as the twist gets tighter, the fibers are squished together. As they are pulled tighter and tighter, the friction between them increases. Both of these things make your thread stronger. Again, I'm saying this is an analogy only to try to understand some of what may be happening out there. You have two threads, okay? Why don't they cross each other? Why do they form the rope? Well, what I say is that right now you don't have any speed. There's no motion of the thread against the thread. It's like lying against that. One thread is just lying against the other, and they're pulled outwards. Okay, they're pulled outwards by what? They're under tension by every atom in the universe, and so between any two atoms, the rope is taut. That's why we have the speed of light is a constant. It's a constant because the tension between any two atoms is always the same. Okay? What changes is the frequency for the wavelength. The wave equation, little c constant, 300,000 kilometers per second, velocity of light, is equal to frequency times wavelength. Wavelength goes up, frequency must come down. Frequency goes up, wavelength must come down. They're inversely proportional. Okay? So the tension between any two atoms on the rope is always the same, and it's measured by the speed of light. That's why the speed of light is a constant. The only thing that changes is the frequency in exchange for the wavelength, and we call that light. We call that colors. Okay, those are the different colors that we get in the visible range, at least. Okay, so what I'm saying is, the threads are just lying against each other and being pulled outwards. That's why they don't go through each other. That's different. That's different than when you have a thread cross another thread, or when you have a rope cross another rope. In the case of magnetism, what you have is many threads. Now you have, again, an emergent property here. Okay, an emergent property that one thread might have a little bit of friction. I can't tell you that for sure. I have to assume it does. It's an imperceptible friction that we would not even be able to measure in our world today. Of course not. But when you put all these threads together, that friction becomes greater and greater and greater, to the point that now, for the first time, you have touch. You created the property of touch, at least in the sense that we have it in our macro world. And what do we mean by that? We mean that you have threads pushing on threads. You have gazillions of threads pushing on gazillions of threads. And now they don't go completely through each other. They do go through each other, but there's a friction when they do so. And that's where the push comes in. The more threads that intervene, the harder it is to put two magnets together. And conversely, you turn one magnet around, now they're both going in the same direction. And now again, you have a little friction there. The threads are going through each other. Okay? And that friction increases the more threads that intervene, which is a function of distance. Okay, I guess you could say an inverse function of distance. The closer they are together, more threads, because more threads are now intervening, and so now you have stronger friction, stronger pull. Okay, so both neutron bombardment or backscattering or any of those experiments, as well as magnetic attraction and repulsion, show you that threads do go through threads. And in the case of neutron bombardment or backscattering, you have ropes going through ropes, but in the form of an atom or a neutron. Okay, and again, remember that the electron shell is made of gazillions of threads coming from every rope in the universe. So it's again an emergent property. In other words, an atom is an emergent property in that sense, that it's made out of the thread, and the thread does not have the same property as the atom, which is macro world touch. Why? Because there's gazillions of thread. Now for the first time you have touch. Until then you have only Mother Nature's touch, which is maybe an imperceptible friction. Okay, so that's how touch comes into being in our macro world. That's the proposal, that's the theory. Okay, I hope I answered to some degree your questions and concerns. Here's another question, comment, okay. Person said, an image of a single positively charged strontium atom held near motionless by electric fields. And there was a picture when you look that up, and it looks like that one there. Guy who won a prize for taking this picture, his name is David Nadlinger. Okay, image of a strontium atom wins National Science Photography Prize. Okay, and so I just want to clarify that we look at that and we say, okay, they took a picture of a strontium atom. Yes and no. Okay. You see two lines there, the red lines that I put in there in the center. I put those, and that's 2 millimeters. That's the distance between the two probes there, the 2 points that were used to hold supposedly the strontium atom in place. Okay, so let's magnify that so we can see what we're staring at. Okay, here's the magnification of that. Looks more or less like that. And so this is what this guy got his prize for. Now, if you look it up, and again, you see 2 millimeters is the distance between the 2 points there, 2 things that are holding the strontium atom in place. Strontium has a diameter of 430 picometers. Okay, and what does that mean? Well, it means that if you look at those 2 millimeters and you divide that by 4.5 million times, you're going to get the diameter of a strontium atom. That's how small it is. So what you're seeing there is not 4.5 million times. You're not seeing the 4.5 millionth part of 2 millimeters. It's much smaller than that. What you're seeing here is a reflection, and that's what the camera caught. The strontium atom is much smaller than what you see there. Much, much smaller. You're talking about gazillions of times smaller. Okay? Because again, it's only 430 picometers. That's the diameter of a strontium atom. Okay? So you would not be able to see one of these. And so the issue here that I'm trying to get to is that we have never seen or taken pictures or imaged an atom, even the biggest atom you can imagine, maybe uranium, more or less stable there compared to the ones that come after. We've never taken a picture of any of these atoms in such a way that we can tell whether it's got a little electron bead going around it. We don't have that kind of detail. We'll never have that. Okay. What we have seen is, telescopic pictures. It's like every time they take a picture, it's from very far away, and it looks like the moon. It looks like a ball. That's what an atom looks like a hydrogen atom, or any of these atoms in general. They have different shapes, but if you take an atom that has an s orbital on the outside, that's a sphere. Okay, and it looks like the moon. So what is that sphere? Where do you find it in quantum mechanics? I mean, according to quantum mechanics, that's not a sphere. What that is a little electron bead that's moving around. What you're seeing is orbitals. Okay? You're seeing a bunch of orbits. So why do we see a ball every time we see an electron? I mean, for it to weave, a ball, it would travel has to travel much faster than light. And that is not the case. An electron does not travel much faster than light to make the ball that you see every second. Okay, so no, an atom does not have a little bead running around it. When they take images, again, bird's eye images of atoms, and again, I'm talking about, just to make it simple, s orbital. S orbital is always spherical. It always encapsulates whatever's inside it, so it doesn't matter. It's always a sphere. And that's our atom. That's the rope model of the atom, a sphere. Okay? What these people are talking about something else. They're talking about a little bead that's going around and forming that sphere. They're saying it's a cloud of electrons. Well, what cloud of electron does the hydrogen atom have? It's only got one electron. Are you telling me that this electron is moving around faster than the speed of light just to make the cloud so that you can take a picture of it? That's irrational. That's what quantum mechanics proposes, and it's totally irrational. That's why Mr. Feynman, Mr. Bohr, Mr. Heisenberg tell you they don't understand their own theory. Okay? On the other hand, it's much simpler. Let's bring William of Ockham, and here's going to tell you choose the simplest hypothesis. What is it? It is a sphere, what you're staring at. What you took a picture of is a sphere. What is a sphere? Well, it's got this whole volume. Okay, it's a shell, it's a cloud, it's an encapsulating membrane. That's what you took a picture of. Now we can make sense of that. What is that membrane? It's made out of the threads. Now we can understand how an atom is built. It's built of threads, not through orbitals, many orbits of an electron. Okay, here on Astronomium, again, this is what this fellow said. He said, just to confirm, just at the bottom it says, I was rewarded with this particular picture of a small pale blue dot. Yeah, that's all you took. That's what do you see there? What kind of detail? Do you see a little electron ball bead going around? Is that what you see? Is that what he took a picture of? An electron bead moving around gazillions of times faster than the speed of light to make that ball? Obviously, that is a ball, not a bunch of orbitals, not a bunch of orbits, not an electron bead that's running around. That's how simple it is. Okay. So yeah, quantum mechanics has nothing to offer. That's why they don't understand it. This is what you got to answer. Okay, here's the quantum atom. You tell me what that yellow stuff is. That's all we want to know. The electron bead, this is a hydrogen atom supposedly, one proton, one electron. Why does the electron bead fall to a lower level and not all the way to the center, where you have the quarks, supposedly 3 quarks from Mr. Mark? And why does it fly away? I mean, why doesn't that electron, I mean, it's orbiting, right? Like if you swing a ball at the end of a string and you let go of the string or you cut the string, well, that ball will fly away. Why doesn't this ball fly away? It's rolling around like a planet. Why doesn't a planet fly away? Why doesn't Jupiter fly away? I mean, what's holding it to the sun? Are we going to do this with spirits, with ghosts? We're going to say black magic keeps the Jupiter tied to the sun? Or are you just going to say, well, it's gravity? Yeah, no kidding. It's gravity. What is gravity? That's what you got to tell me. Not tell me that it's gravity. Okay. Okay, another issue, another question, another comment. Here we go. Another fellow says, he says, you can't point to your shadow. No, you can't. Not in science. In ordinary speech, you can say anything. You can say love moves mountains. And you can get away with that because nobody's paying attention to any of the details and whether you make sense or not. In physics, we have to make sense. And no, we got to find out what a shadow is. What is a shadow? It's blocked light. Blocked light is not a physical standalone object. What blocked light is a concept. That's why we define it and we see shadow is blocked light. Okay, so now we know what, not a what, but we have the concept known as shadow. It's not a physical object. It's a concept because we defined it, and you can't point to a concept. And you say, well, I pointed to the shadow, to that shape. Yeah, but the shape, there is no shape because the shape includes you. The shadow starts at your feet. You are part of the shadow. You can't separate the shadow from yourself. See, if we could separate the shadow from you, that would be great. Then we could say it's got shape on its own. But see, the shadow, the feet, like when you put a light on you, the shadow goes all the way to your feet. It's stuck to your feet. As soon as you pull the shadow out, we'll know if it's an object or not. In physics, not in ordinary speech. Okay, and so in physics, shadow is not a standalone physical object. Physics, we point to objects, okay, and define concepts. And that's what shadow is. It's a concept. That's why we define it. And you just follow the definitions, and I promise not to bang you with my baseball bat. Okay, and here is just the icing on the cake on that one. Okay, Let's get it up here. Objects we point to. Concepts we define. Okay? So that's black and white. Okay? It's on or off. Yes or no. Okay? And it's the third principle of physics. You can't point to a concept. So if you said that you can point to a shadow and your shadow is black light, a concept, then I don't know what you're pointing to. Maybe you're pointing to the floor. You say, no, it's my shadow. Well, how can you point to something that doesn't have shape? You say, it does have shape. See, it's got shape. Well, shape is all around, and I can't see it all around because your feet are in the way. Okay, an issue on ether. A couple of people posted something on ether. Fellow says, the ether is not a bunch of particles because it's intangible, pre-hydrogen matter. I don't know what all that means. And another fellow says, ether is particles. What do you mean it's particles? Well, yeah, all you guys have to do is define ether. Once we know what the definition of ether is, then we'll know what you're talking about. And hopefully if you define ether, it means not a physical object. Because again, what do? We define concepts and we point to objects. And that's the ether, okay? And it's not an object because I can't point to that because it's moving. Okay, it's moving all around. I see a bunch of particles and you say, well, what particle are you pointing to? To that one, the one that just moved. So, no, you can't point to ether. You can't point to ether because ether is the definition of ether. It's a concept because we define it. It's a bunch of particles. And which particle are you pointing to? That's the object, not the ether. Okay, so ether is a bunch of particles. You don't like that definition? There's what you got to do. You got to define the word ether. Don't tell me what it ain't. Everybody likes to tell me what it ain't. You say, you got it wrong, Bill. It's not a bunch of particles. Okay, what is it? Please define the word ether. Until you do, you're just spinning your wheels. You haven't said anything. You got to define the word ether. I mean, if you're going to use it, if you're going to say that your theory depends on the ether, like maybe Ken Wheeler does. He says it depends on the ether. You have the people in the John Chappell movement. I call them the John Chapel. They're etherists as well. Okay, what is the ether? You know, when I told one of these guys from the John Chappell group that ether was a bunch of particles, immediately he said, no, that's not what an ether is. Don't tell me what it ain't. Tell me what it is. You can say, Bill, you're wrong. Okay, what's right? Tell me what it is, not what ain't. And no, you'll never find anyone defining the ether because as soon as they do, it's very easy to tear them to pieces. Okay, that's why they don't define it. Oh, I want them to define it so that I can have a chance. Give me a chance to bop them. Here it is. This is what I'll use. My dough roller. Okay, next question, next comment thing. What does this guy say? Okay, a square is an object because you changed the definition to an object is that which has shape. Yeah, not that I changed it, I circumscribed it because that's what a definition is. It's a limitation placed on the extent and or usage of a word. And so I define the word object as that which has shape, okay? And there we have I think that has shape, it's a square. And if you don't like that, well, you got to define the word object. Very simple. I mean, if you can't define the word object, you haven't said anything. All you said is you don't like my definition. Great. Tell us what your definition is, and maybe you got a better definition than I do. I'm always looking for someone who's got a better mousetrap or invented a better mousetrap than me. Okay, another issue, comment. Fellow says, light doesn't slow down through a transparent media? Yeah, it doesn't slow down. See, you got the equation there. Velocity of light equals frequency times wavelength. Velocity of light is always 300,000 kilometers per second. Always, no matter what light goes through, because light doesn't go through anything. Light goes through things only in the religion of quantum mechanics. In quantum mechanics, yeah, you have one-way mechanisms such as waves and particles. Waves are not physical objects. Waves are just a bunch of vectors. They give you the idea that you're talking about something when they're only vectors. Okay, they don't have a physical object called a wave, transverse wave, or longitudinal wave, or whatever. There is no standalone object called wave. Wave is a verb. Okay, and as such, it's a dynamic concept. Therefore, there's no such thing as one-way travel of a wave. And the other one is the one-way travel of particles. Well, in the case of classical mechanics, we could understand it because they're talking about corpuscles. Okay, and we cannot explain under that definition, that notion, we cannot explain wave phenomena. Okay, you cannot explain frequency. You cannot explain wavelength for sure with particles. And you cannot explain why the particle goes up and down to create that wavy motion. What pulls the particle up? What pushes the particle down? That's what you got to explain. And if you cannot explain that, I mean, why would another particle follow another one? Like one particle goes up, the other one goes right behind it to create that sine wave. Well, hold it, we got a problem because, is it pulling it? Is one particle pulling on the other particle? Is that what makes the sine wave? Why does one particle follow another particle? Are they tied together like in a string? I mean, we can understand this. If I move this around, you say, well, I see why this portion follows that portion because they're all tied together. How do you do that with particles, with discrete particles? So yeah, those two mechanisms at the top that are the ones proposed by quantum, those are one-way mechanisms first, and that's always a big problem. Particles you cannot explain. Classical particles, again, I'm talking about here, okay? Classical particles, you cannot explain wave phenomena, wave properties of light. And then under quantum, you don't even have particles. What you have is concepts, and they're moving concepts around. They're saying a wave is, or a particle is just a number. So they're moving numbers around, quantities, amounts. It's like moving your bank account around. So no, we have a physical object. We're saying it's a rope. And what we have is torsion. Okay, torsion of a rope. Okay, this is what we have. And, the more you torque a rope, the smaller the links become. And the less you torque a rope, the longer the links become. And you have, fewer links. And that's what color is. And that's why when the light goes through a prism, we have different colors coming out, not because light is traveling at different speeds, but because we've traded frequency in exchange for wavelength and vice versa. That's what color is, different wavelengths. In other words, links under the rope model. So yeah, there is no traveling of light. Light doesn't travel anywhere. Light torques in situ. And what we're looking at is different lengths of links. That's it. And that's what gives you the color. So light always travels at the same speed between any two atoms. It's always 300,000 kilometers per second. Again, that's very close enough number. We don't need to know the exact value of light, the velocity of light, like Michelson spent his whole life measuring. Got a Nobel for that. That's not science. That's measurement. Measurement is not science. Science is explanation. Okay, observation isn't part of science. Then you drop a pen to observe. Yeah, I dropped a pen the other day. Okay, so he's saying that you let go of the pen, yeah, and he said that's observation. And experiment isn't a part of science. Then you cross two flashlights, like I did a minute ago, asking what did you observe? No, I did not ask what did you observe. That's what he got out of it. I don't ask that question. What we have is this. This is the context for the word observation, why we do not have observation in science. And let me put it over here on the, left-hand side. My left-hand side, your right-hand side. Okay. It says, in the religion of mathematics, okay, observation is used as a weapon. That's what it is. It's a weapon. Okay. And what do you mean a weapon? Well, observation means experiment. It means measurement. Okay. It means evidence, proof. Why did you do an experiment? Well, because you're going to prove to someone that your theory is correct. Whatever explanation you gave, you're going to back it with evidence. What is evidence? An experiment or an observation. Okay, and what is an observation? Well, so far all you have is a description. All you did is gawk. Until you can explain something, you haven't said anything. All you said, yeah, the car went down the hill. And you say, okay, why did it go down the hill? Oh, I don't know. I just saw it. I observed it going down the hill. All you're doing is testifying that you saw something, you describe it, but you have no explanation for the phenomena. So that's why it's not observation. That's the context, okay? It's got to do with perception, which means it's subjective. It's used to persuade, convince the jury, okay? And it's used to convert and recruit. It's only to get the jury to believe like you do. That's why we do, that's what they use observation and experiment for. Okay? That's why we don't have any use for observation in science. In science, we say, and again, you see the examples there of another issue, which is that, did Stephen Hawking ever observe, like with his eyes, did he ever observe a black hole? Did Rutherford ever observe the empty space inside an atom? This doesn't mean that they cannot make an assumption and they say, let us assume, which is what they're doing really. They say they proved it, but that's their opinion. Let us assume that an atom has absolutely nothing inside it between the proton and the electron. That is mostly empty space. Then you make an assumption. You didn't observe, you just make an assumption to explain your theory. And you say, now I can explain this with that assumption. That's the way it works in science. You make an assumption. You don't have to observe and say, I observed. So you can't call me a liar because I observed with my 2 eyes. No, that's not scientific. In science, we say, let us assume that God exists. Now you can continue with your theory of how God created the universe. But you can't say, oh, God exists, I proved it, and here's the evidence. The evidence is in the Bible. No, you can't do it in science. In science, it's unfair. It's irrational. Okay? What we do in science, we make an assumption. And so we don't need the word observation at all. You don't, because observation is what it says there, testifying. It's saying that you're going to bring subjectivity to your presentation. You're going to try to convince the jury that your eyes did not fail you. With that, I'll see you on Sunday, and we're going to have my son here, and I'm going to open the floor for questions. So it's going to be live. Whatever questions you may have, we're going to try to address them right on the spot. Again, sometimes there are too many questions. We can't address them all, but we'll try to address as many as we can. Okay, so my son Hans is going to be here, and we're going to try to have a good show for you. So get your questions ready. Anything you want to throw mud pies in our face, do it. No problem. We can take it. We got thick skin here. We'll see you on Sunday. Bye-bye.